Hi everyone. Good morning, good afternoon, and good evening, depending on the time zones that you are in. We are extremely glad to welcome all of you to the seventh talk of the monthly colloquium series by CARINAS. We are very delighted to have Professor Priyanka Singh as our today's colloquium speaker. Before starting the talk, I would like to say a few words about this forum, CARINAS. CARINAS currently has more than 250 Indian researchers working in astrophysics and related fields, with 41% within India and 46% currently studying working abroad. And 87% of our members are early career researchers who are in the formative stages of their careers. These are the stages in which we start losing women researchers from academia due to various reasons. This forum's goal is to empower these early career women researchers in India and first generation Indian women researchers outside the country through networking, support, mentorship, knowledge sharing, and collaboration in any way possible whenever it is required. And among our initiative towards reaching these goals, we have started a newsletter series where we are not only focusing on the great sciences done by women researchers, but also their life experiences in academia. We have already published two editions covering fascinating and inspiring pieces. You can explore these editions on our website, carinas.co.in. Another initiative of CARINAS is this monthly colloquium series, where we already have six great talks. Now the time for the seventh one. Without further ado, I invite Monami, who will introduce our esteemed speaker for today's colloquium. Thank you.
Thank you, Mummy, for the introduction. It's my great pleasure to welcome Priyanka for CARINAS colloquium. So Priyanka is currently in IIT Indore as assistant professor. Before that, she was a postdoctoral fellow at Yale University. She did her PhD from Raman Research Institute, and then after that, she joined INAF, and after that, she joined Yale for the postdoctoral fellow. She works in circumgalactic medium and different aspects of observational studies of the circumgalactic medium, especially SZ effect. And I would like to invite Priyanka for our talk, and yeah, take it over.
Thanks a lot, Manami, for the introduction, and hi, everyone. I would like to start by thanking the CARINAS team for inviting me and giving me this opportunity to present my work in the colloquium series. And I would like to grab this opportunity by advertising a recent work on understanding galactic ecosystem from the point of view of circumgalactic medium, which Manami just described has been my research field for the last decade or so. So here's a brief outline of what this talk is going to be about. So it is about galactic ecosystems from the point of view of the circumgalactic medium. Now, galactic ecosystem, when I use the word, it may mean different things to different people depending on their area of expertise. So I'll try to explain what I mean by the word when I use the galactic ecosystem and its connection with the circumgalactic medium. I'll start by explaining what the CGM is, what makes it so interesting, and how it plays an important role in the galactic ecosystem. Then I'll move on to our work on the multimodal or multimodal analytical modeling of the CGM. And I'll conclude by presenting some results on multiwavelength predictions or the multiwavelength tools that can be used to constrain the properties of the CGM. Before starting the talk, I would just want to say that let's keep it informal. Please feel free to stop me whenever you have any doubt, and I'll try my best to reply to your queries. Yeah. So according to one of the most successful models of cosmology, the lambda CDM, when a galaxy or a galactic halo, I'll use these two words interchangeably. When a galactic halo is formed, it contains around 84% of its mass in the form of dark matter and roughly around 16% of its mass in the form of baryons. A good fraction of these baryons, they cool down, they condense to the central part of the galaxy, and they form stars, therefore they shine in optical light, which forms this central optically visible part of the galaxy. But a good chunk of these baryons remain too hot to condense to the center, and they form this fraction of the baryons, they form a diffuse gaseous medium surrounding the central optically visible part of the galaxy. It may occupy a region which can be as large as 10 times the size of the central region. This is what is known as the circumgalactic medium. And when I use the word the CGM, this is the gas I'm referring to, a volume-filling, warm, hot gaseous medium, which is gravitationally bound to the galactic halo. Okay, now to put things in a more theoretical perspective, and also like to define boundaries, the word CGM or the gaseous halos referred as CGM, they are generally associated with galaxies with masses less than 10 power 13 solar mass or so. So this mass is the total gravitating mass, and the gaseous halo surrounding such systems is called CGM. The sizes can be of the order of a couple of 100 kiloparsecs or so, again, depending on the size of or mass of the galaxy. For example, our Milky Way lies in this regime. Its total gravitating mass is of the order of 10 power 12 solar mass or so. And the gaseous halo in our galaxy, the Milky Way galaxy, is the CGM. When we go to higher mass scales, 10 power 13 to 14 or so, we are in the region of regime of the groups. And the gaseous halo in these systems is referred to as intragroup medium, with sizes of the order of like 500 kiloparsec or so. These are all ballpark numbers. On the extreme, other mass extreme, we have galaxy clusters with masses more than 10 power 14 or so. And the gas in these galaxies is referred to as intracluster medium or the ICM. And these systems have sizes larger than megaparsec or so. Again, CGM, intragroup medium, ICM, these are all gaseous halos, which are, in a way, you can think of it as the leftover of the star formation. And the properties are determined by the total mass of the system. And they're theoretically the same thing, defined in this way. For example, it's not just the sizes, it's also the temperature, which varies by from 1,000,000 degree Kelvin in case of the CGM to 100 million Kelvin in case of the intracluster medium. Basically, the property of this gaseous halo is determined by the host in which it lives in, and mostly the mass of the host in which it lives in. So just to recap what the CGM means, it is the gaseous halo which is gravitationally bound to the galactic halo. It occupies a much larger volume than the central galaxy, and it contributes significantly. It can contribute significantly to the baryon budget of the galaxy. This is roughly how a CGM, a hot gas CGM, can be defined. Now let's talk about this galactic ecosystem and the connection of the CGM with galactic ecosystem. We have been talking about this galactic halo and the CGM. it doesn't sit in isolation. Our universe is filled with the intergalactic medium. This is the gas between galaxies, IgM. And since a galaxy is a gravitational potential well, it will attract more material onto it due to its gravity. And there'll be a accretion, a continuous accretion of fresh material onto the CGM. The CGM will also be accreted onto the central part, and it will act as a fuel for the future generation of star formation. Now, these stars, many of the stars which are formed in the galaxy, they are massive enough to undergo supernova explosion, thus ejecting a huge amount of energy and material into the CGM. And depending on the power of the explosion, on the power of the supernova feedback, the material can be pushed even beyond the gravitational boundary of the galaxy, the virial size of the galaxy. At the same time, almost every galaxy in the universe has a supermassive black hole at its center. And these supermassive black holes, they undergo this active galactic nuclei phase. And when they are in this phase, they can also eject huge amount of energy and material into the surrounding. And again, feeding back into the CGM and maybe even beyond. So together, there are a number of very interesting physical processes happening. They are interlinked, and all of them are equally important. And CGM lies right in the middle of these really interesting processes, which makes it a key component of galaxy evolution. Now, the CGM is also linked, understanding the CGM is also linked to cosmology through the missing baryon problem. Just a few slides back, I mentioned that lambda CDM predicts that 16% of the baryons should be in galaxies. But when we point our telescope towards these galaxies, we don't find these baryons there. We find more or less half of the baryons in these galaxies. The other half, roughly the other half of the baryons are observationally missing. And that is what is known as galactic missing baryon problem. So why are these baryons missing? Where are these baryons? So there can be three explanations of this missing baryon problem. The first one, which is least likely, is, are the cosmological predictions wrong? Maybe the galactic missing baryon problem is not a powerful enough tool to say observation to say that. But the other two explanations are probably more likely. For example, maybe these baryons are thrown out of the galaxies. I just discussed this powerful feedback processes, the supernova and the AGN feedback. It is possible that during these feedback processes, a lot of this gas is pushed out of the boundary of the galaxy. And that's why we are not able to see that. The other explanation is maybe there is no missing baryon problem. It is just that our telescopes are not sensitive enough currently. And maybe in future with better telescope, we'll be able to see this gas within the galaxy. That is another explanation. And just to bring back the gaseous halos and the theoretical definition of the CGM, it should be same as the ICM in clusters. And we don't see any missing baryon problems there. So, which also indicates that this 0.1 is most likely not the reason. It is one of these two reasons, because intra-cluster medium, this is the gas in clusters. Yeah,
I will stop you. There are a couple of questions in the chat.
Sure, of course.
So there are two questions that if this CGM contains dark energy, and second question is, what are baryons?
Okay, so dark energy, no, the CGM is just the normal matter. and baryons are also just the normal matter. So baryon is a very broadly used term. Normal, even leptons are normal matter, but most of the mass, proton, for example, most of the mass in the universe is, most of the material in the universe is in hydrogen, right? 75% of the universe is hydrogen, and hydrogen is, within hydrogen, it is proton, electron. So most of the mass in the universe is in the form of like protons or baryon. So it's very loosely used term to describe the normal matter. So baryons are just the normal matter. And I'm not going to go into like, there is a like particle physics definition of baryons. I'm not going there. I'll just call it normal matter. There is no dark energy there. Yeah.
Thank you. I'll then, whenever people post question, I'll then maybe stop you and
Sure.
ask you the question. Okay.
Sure. Okay.
Thank you.
So yeah, I was talking about the intracluster medium, and let me take you to the slide where I describe the intracluster medium. So I mentioned that it is the property of the host which determines the property of the gaseous halo. And intracluster medium, you see the total gravitating mass, 10^14 solar masses. It is very, very massive system. So you can imagine the kind of gravity it will have. And for any kind of feedback processes, so this kind of like feedback processes won't be as important in case of galaxy clusters, because the gravity is much stronger there. And therefore, to say, on the other hand, in case of like galaxy like our Milky Way, which is a small galaxy with like 10^12 solar masses or so, here, there the feedback becomes important. It becomes comparable to the gravitational forces in the galaxy. That's why we think current knowledge about the galactic ecosystem and how the galaxy evolution, we believe that it is most likely that these baryons are probably thrown beyond the boundary of the galaxy, but the item number 3 is not striked out completely yet. Okay, fine. The third point which makes the CGM extremely interesting, especially for me, is it is very poorly constrained. The mass in the CGM, the temperature of the CGM, you name the property, it is very poorly constrained in this field, which creates a lot of scope for new discoveries, new challenges, and which is what makes it one of the fastest growing subfields within galaxies. And that's one of the reasons I'm really attracted towards this field. And with that, I'll move on to the work that I've been doing in past couple of years and how I'm trying to tap into this part. I'll try to explain. So I've been working on the analytical modeling of the CGM. And to be more specific, we are working with like very simple 1D models to constrain the CGM physics. So one may ask that in the era of hydrodynamical simulations, why are you using the analytical models, right? These simulations are really like sophisticated and all. So why to like bother with this really simple spherical curve models? The answer is these models are still these models are something which a human brain can more easily like understand, because they're very intuitive, right? Simulation, there are like 100 different things happening. And if you see one feature in the simulation, it is almost impossible to tell what is the reason behind that feature, unless you vary the parameter and run the simulation maybe 100 or 1,000 times, so that you know what is exactly happening, what is the parameter that is driving that feature in the simulation. But it is very computationally expensive. Even to run one simulation, it takes months. So you can't really run it for like 100 times or so. But these 1D analytical models, these are idealized simulations in a way. So they are easy to use, they are intuitive, which makes them for human brain too easy to connect with. And with these analytical models, we can try to capture the dominating physical processes. We can maybe choose one or a few dominant process which we think is the most important for the CGM, for example, and and we build our model on top of that. So that's why we are still working with like analytical modeling. We think that it is still a very powerful tool. And in this particular work, what we have done is we have compiled several popular analytical models of the CGM into a single Python pipeline. And the reason behind putting effort into creating this platform was we're trying to minimize the cosmetic differences due to the different input ingredients in different models, so that whatever outfit features we are seeing, predictions we are seeing, we want to make sure it is due to the different modeling assumptions, not due to any cosmetic differences. And ultimately, the Python pipeline should be easy to use for the community, and it should be easy to modify in the future. So that's the theoretical motivation behind this work. And on the more observational front, these are the two questions which were asked in a conference that I attended last year, Oasis and Cosmic Desert. And I think this work really resonates with these questions. What are we doing to leverage our observational capacity to better prove the CGM as a community? So what are we doing as a community to pause and think what is the better way to move forward, and creating a single Python pipeline where you have several different models that you can play with is, I think, a good step in that direction. So what is analytical modeling of the CGM? We start with these three equations. It is nothing but the conservation of mass, momentum, and energy or entropy. So all these different models, they're trying to solve these three equations. The difference is how they solve these equations. What are the assumptions which are made while trying to solve these equations? I'll explain it in a moment, but before that, I'll talk a bit more about the pipeline. So even though there are there can be different assumptions in different models, there are still some common ingredients in this equations. For example, there's this gravitational potential term, which can be homogenized amongst different models. There is the implementation of cooling, which again can be homogenized among the different models. The boundary conditions which are used to solve these equations should be homogenized amongst these models. So this is what this pipeline does. It creates this gateway to have the same set of input ingredients. And then you choose your favorite CGM model from the pipeline, which we call the systematic comparison of analytical models. You give it input parameters, you choose your favorite CGM model, and the pipeline gives you the thermodynamic profiles of the CGM. By that, I mean density, temperature, pressure, mass, etc. All these like different profiles of the CGM. So this pipeline is publicly available, still in very, very beta version on this GitHub page. We are still working on it. We are trying to make it as user-friendly as possible, trying to incorporate as many output options as possible. You can also scan this barcode and go to this link if that works better for you. Fine. So now coming back to how these different models solve the conservation equations. One of the first models that we involved in this pipeline is the precipitation model, which is led by Mark Voigt. So how it solves the conservation of momentum is it assumes hydrostatic equilibrium, which is actually one of the most commonly used assumption in most of the models that you'll see out there on arXiv. Then to solve the entropy conservation, this particular model, the precipitation model, it invokes this ratio. This is the ratio of two time scale, free fall to gas cooling time scale. Okay. And this ratio is inspired by a particular set of observations. So in observations, people see that this ratio provides an envelope, an upper limit, and none of the systems that we observe in the universe go beyond a particular limit of this ratio. So that's what they use in this model. And they assume that the pressure is only thermal pressure. There is no non-thermal pressure. They provide gas temperature boundary condition to solve the set of equation. Manami, are there any questions? I can take a pause here.
I think there is no question in the chat. There was one. I think you already answered that. That is the Python pipeline available on GitHub or any.
Okay.
Yeah, I think one thing maybe I have a question maybe. So so can you talk a little bit about why we choose this the value for, I mean, why this ratio value is kind of like this, not like larger than that? Is it possible to have a large?
Yes. So this is assumption. Okay, this is the modeling assumption using this ratio of T free fall to T cooling time scale equal to 10. That's what Mark White and the series of paper put forward, that this is okay. This ratio provides the maximum limit to a particular scaling relation, and there's a minimum value of this ratio, which provides an envelope to a scaling relation. But there can be a range. Okay, there can be a range. It's not one value, but it is, they assume that this ratio is fixed within the galaxy. Again, it's a simplified assumption. There are models which relax it. But if your model is so simple that this ratio is radially independent and it still provides a really good match to a number of observations, why to make your model more complicated?
Yeah.
That's the, your observations should be able to tell the difference between this model and a more sophisticated model. Why to make your life more complicated if your observations are not able to tell the difference? Speaking very, very roughly, but there are models. I'm familiar with other models which have, which probably don't use exactly this particular ratio, slightly different combination, maybe not exactly radially independent. There are efforts in that direction as well. Yeah.
Thank you.
Sure. So the other model which is there in this package is the isentropic model, which is led by Yakov Fireman. Again, this model uses hydrostatic equilibrium, and to solve the entropy equation, entropy conservation, what they assume is the entropy is fixed. The entropy is radially independent, and that's how they solve this equation. And another very interesting thing about this model is they allow for the presence of non-thermal pressure. It is not just the thermal pressure. There is turbulence. There can be something from some sort of pressure from magnetic field, cosmic rays. So they allow for the possibility of like a range of different contribution from different components in non-thermal pressure. I won't go into the details of each of these models. A lot of them are not I'm not directly involved in, but these are the 4 models which are currently the part of this package. And if you are interested in the details, the technical details of these models, please feel free to ping me after this talk. We can chat more about it. Okay. But again, to summarize, we have this package which is publicly available. Currently, there are these 4 models in the package, but it is not meant to be just 4. If you have your own, if you're working in this field, if you have your own CGM model, please contact me. I would love to add a 5th model. The package is meant to be flexible enough to have another model, any n number of models into it. Okay.
We have a question in chat that a question is asked by Sharanjit Viswas, which is TFF by T-cool means. I mean, what does TFF by T-cool means?
So T free fall is the free fall time scale. Speaking very roughly, if you let your halo collapse under its own gravity, if you let your galaxy collapse under its own gravity, how much time that takes is the free fall time. And T cool is the gas cooling time scale. You have the CGM in the in your galaxy, right? How long does it take to cool down below a certain limit? Yeah, these are 2 time scale, and somehow the ratio becomes important in this in the observations of the CGM. And they're still exploring what is the exact origin of why this ratio is important. Yeah.
Okay, thank you.
So here is a pictorial, very like schematic pictorial representation of these 4 models. Again, I won't go into the details of this. If you are interested, please feel free to ping me after this talk. I'll jump to the results. So this is the output of that package. I was saying, like, you give it some input. So what we have given is these homogenized input conditions amongst the 4 models. And this is the output of the pipeline. Here I've shown the entropy, thermal pressure, electron density, and temperature profiles for the 4 model, for their fiducial 4 model. And one thing which is probably some of you can notice that most of these models kind of converge at some intermediate length scales. It is only near the center of the galaxy and the outskirts is when you see any significant difference amongst these models, which means that we need not just one, multiple radially resolved thermodynamic profiles to be able to tell the difference between different models. And the meaning of telling the difference between different models is telling what governs the CGM physics, what is happening in the CGM. Precipitation model assumes something different. Isentropic model assumes some other different physics happening, different physics. Like, by different physics, I mean, like, is the entropy constant, how the feedback affects the CGM and all these things, how that is encapsulated while solving those conservation equations is what we are after. And our ability to differentiate between different models means our ability to tell what is the physics that governs the CGM. Okay. Now, let's talk about the multi-wavelength part of the multi-wavelength predictions coming from the 4 models. So this is another package, Python package created by Irwin Lau, who is one of the lead authors of this paper. Here is the barcode. You can scan this, and which will take you to this web page. Again, this is public. It's called CGM Toolkit. And what it does is you can provide it any set of like thermodynamic profiles for your own models, and it will give you a set of observables, right? Let's say if you're working in the SC, the Sineev-Zelder effect, then you can use this pipeline. You can provide your own model, your own density, temperature profiles, pressure profile, and it will tell you, it will give you the projected 2D projected Y profile or thermal SZ profile, or there are many other options as well, and I'll only show 6 options today. So let's focus on this first panel. This is thermal SZ as a function of impact parameter, that is the distance from the center of the galaxy. And this is 2D projected. So we are viewing the galaxy as an external observer. And this is the property of the galaxy. So we are assuming that the galaxy is like our own Milky Way in the local universe. And this dotted line here represents the sensitivity levels which can be achieved by CMB S4 like mission. So CMB S4 is what is one of the best possible CMB missions which is planned today. So if it happens, this is the kind of sensitivity levels that we'll get by stacking a large number, like 300,000 galaxies. And you see that for these 4 fiducial models, we should be able to detect the thermal SZ profiles out to around 100 kiloparsec or so for this kind of galaxy. Okay, this is good, but you see the differences between different models is not very large. So it was a bit disappointing when I first saw this figure, but still, like, it's encouraging that one is able. So one should still be able to discard a lot of other models, a lot of parameter space, which is not shown here, by using the thermal SZ. I'll take a break. Just give me a second. Now, what came as a surprise out of this work is shown in the bottom panel. So there are 2 observables, not one. In this bottom panel, there is dispersion measure and there is kinetic Syniav-Zeldovich effect. So anyone who works more or less in the field, can someone help me in explaining why I have plotted these 2 observables in the same figure? Come on, any wild guess? Why kinetic SZ and the dispersion measure are equivalent to each other?
Because, I mean, both related to pressure of the CGN.
Pressure is actually thermal Syniav-Zeldovich effect, but you're going in the right direction. You're thinking in terms of thermodynamic profile. So both of them trace a particular thermodynamic profile, which is not pressure, but you're close.
Density.
Yes, density. So they are both the column density, line of sight integration of the density profile. So that's why I plotted both of them in the same panel. And the dotted line here corresponds to a stack of 100,000 galaxy for CMB S4 like specifics. And you can see we get really great sensitivity level. And if CMB S4 takes off, one should be able to detect the KSC signal from these galaxies out to the virial radii, which is amazing. So, which actually highlights the importance. This result highlights the importance of kinetic Syniav-Zeldovich, kinetic Syniav-Zeldovich effect in exploring the galaxies like our own Milky Way in the future with CMB missions. In this middle panel corresponds to the surface brightness, X-ray surface brightness profiles, and this dotted line here corresponds to the sensitivity level of eROSITA mission. The ERAS corresponds to eROSITA All-Sky survey for a stack of 70,000 galaxies. And the results are again not very encouraging here, because for a galaxy with this specifics, you can detect the CGM only within a few tens of kiloparsecs. But again, this result highlights the need of like much more sensitive missions than ERAS, so that one should be able to observe galaxy outskirts, which is where the difference between the model really shine. In this right panel, what I have shown is different column densities. Oxygen 6, oxygen 7, and 8. These are regularly used in the field of CGM to constrain to constrain the CGM physics. And again, in oxygen 6, you see stark difference between different models, which shows its power to differentiate between to be able to constrain the CGM physics. And again, the sensitivity level correspond to the best, one of the best missions that we could find in literature, which is planned or COS halos is already done. So this is so this figure mostly has, I think, other than COS halos and ERAS 4, which is already done or ongoing. This is mostly predictions for the future missions and in forecasting that we should be able to detect the signal down to like out to this much of galaxy size, this kind of like signal. What about the current observations? Now, I'll show some current observation and I'll also give some caveats when you're comparing with the observation. So let's focus on this first panel here. It shows one of the latest observations of thermal Synev-Zeldovich effect from L-star galaxy. By L-star galaxy, it means the luminosity is similar to the Milky Way galaxy. And you see them all these different models, like these are 4 models, which are built by 4 very different people sitting on 4 different corners in the globe, right? And all of them are an order of magnitude below what the data says. So what we think is happening here is Malmquist bias is one of the reasons behind this. And what is Malmquist bias? When you're stacking the data, which means when you're averaging the signal, it is dominated by the brightest galaxies. It is dominated by the brightest object. You're looking at the average, whereas this is the median. So this is one reason why it's happening. And another reason is when people say L-star galaxy, what do they even mean exactly? For them, L-star could be twice or thrice as massive as the Milky Way. So when one is comparing with the observation, one has to be very careful. We should create an exact, like we should match the sample in terms of mass, in terms of redshift, to be able to properly compare with the data. Okay, so this was the story about the TSC. And in this bottom panel, I've shown these 2 triangles, which are the upper limits for the latest dispersion measure for our own Milky Way. So this is probably one of the best direct comparison of these models with the data, because this is for our own Milky Way galaxy. And because these are currently upper limits, all the models are consistent, but it is nice to see that they're not too far off from the model predictions. Now, looking at the absorption column densities, it is really interesting to see that these COS halo data points, the distance between the COS halo data points and a lot of these models. And again, the problem here is these data points span a range in mass, a range in redshift, and we can't really compare it one fiducial model. We should first match the mass distribution, match the redshift distribution, and then only compare with this kind of data. But these 2 data points are for Milky Way galaxy. So you see here, there is a decent agreement with oxygen 6 and these models. but oxygen 8 is somehow way above compared to these models. And which is where I would like to highlight that none of these models have been tuned to reproduce this data, which so even though these models are not tuned and we are still not too far off, is still encouraging, and which again creates a scope for a future work where we try to fit a bunch of different data sets, not just one data, to be able to discard or to be able to verify a given model and hence a given combination of physical processes that are affecting our galactic ecosystem. With that, I would like to summarize. And before summarizing, I would like to highlight this, again, the set of questions, which is probably one of the motivating factors behind this work. What are we doing as a community in this field? And I think taking a pause, like all these people who were involved in this project, they took a pause, they came together to create this pipeline, which should be useful for the community and especially for the young scientists, for checking, for playing around with these models, for exploring this field. I think it's a really good starting point. And now I would like to summarize. What we have found, this part was expected actually, that we need radially resolved profiles because it is only at small and large radii where we see the differences, significant differences in these models. What came as a surprise was the importance of KSC, and we think that this is the direction the people working in the CGM should push. We should slowly not stop thinking about, we should not give too much focus to TSC and start thinking about the KSD signal, as it looks really promising. And it is not probably not just one wavelength or one probe that will solve the problem or that will answer our question. It is the multi-wavelength approach that is required, because each of these models have really unique, they are unique in different wavelengths, and it's the combination which is very interesting, which can be used to either verify or nullify these models. And before stopping, I would again like to advertise this pipeline. Please go use it. Let me know if there are any issues. This is still again in very beta phase. And if you have your own CGM model, please get in touch with me. I'll try my best to add it to the pipeline. Thank you for listening to me and giving me this opportunity. Thanks a lot.
Thank you, Priyanka, for this lovely talk. And it was great to hear all about circumgalactic medium from you. So any question from the audience? Feel free to unmute yourself and ask. And if you are not comfortable, you can ask in chat. I can ask it for you.
Can I ask one question?
Yeah, sure.
Yeah. Hi, Priyanka. It was a nice talk.
Thank you.
I have just one question. Can you just explain the process of CGM, circumgalactic medium?
Mm-hmm.
And you said that in the beginning, in the galactic halo, there is 84% of dark matter, and you did not mention about dark energy.
Oh, because I was talking about mass. So
Okay,
I was not talking about the energy budget. I was talking about the mass budget of the universe. So that's why
Okay.
this 84% mass and 16% by mass. Yeah, I didn't mention, I was only talking in terms of mass.
Okay.
That how
Yeah,
much
thank
mass
you.
that we expect in baryons from lambda cerium. And even that we are not able to see in galaxies like Milky Way.
Okay, the circumgalactic medium means it is gaseous, I think, around the galaxy, right?
Yes.
As per my understanding. Can you just
Yes.
throw more light on this?
Yes. Let's say our own Milky Way. We have of the order of like 20 kiloparsec diameter of the disk.
Yeah.
And the size of the halo, the size of the circumgalactic medium is 250 kiloparsec. So it is 10 times the size of the central
Yeah.
disk, but it is
Okay.
gravitationally bound.
Okay.
They are all gravitationally bound together, and the property of this gas is determined by the property of this galaxy, which is sitting at the center, the stellar mass and the mass in the gas. They are also like very tightly linked. So that's why it's a galactic ecosystem, because you can't have just a random mass or a random property of the CGM and a random property of the central disk and the black hole actually.
Okay.
Even the black hole here, the mass of the, there's that slide. Okay. The mass of the black hole and the properties of the CGM, even they are very tightly linked. So that's why it's an ecosystem, and everything like controls, all these processes are somehow controlling each other. Yeah.
Okay. And so basically, what are those models? You explained few models. So exactly what is the role of those models?
So let's say I want to, there's this observation, X-ray brightness of the CGM. Like if I observe a galaxy, Andromeda galaxy in X-rays, I see that there is a hot diffuse gas much beyond the central disk of the galaxy. And now I want to understand its properties. So the one thing I need to be able to match with the observation is its density and temperature, right?
Okay.
Surface brightness is roughly density square and a function of temperature. So how do I get the density and temperature? All I know is probably the stellar mass. Maybe if I have some velocity measurements, I even know the total mass, means dark matter plus the baryons. I know the total gravitating mass. But how do I connect that with what I see in the X-rays? Because that X-rays is coming from the CGM. So I need the density and the temperature profile. And that's what these models give. So that's how these models are useful in understanding what is the condition around the galaxy. Let's say if I have a model which gives me a temperature of like 10,000 Kelvin, a 10,000 Kelvin gas won't shine in X-ray. So I know that that model is wrong because I can see an X-ray emission.
Yeah. Okay.
I hope that. Yeah.
Yes. Yeah. Thank you, Priyanka.
Sure. Thank you.
There is another question in the chat by Shanjit Vishwash. Cosmological prediction are wrong was in one of the slides mentioned. Mostly cosmological predictions are based on boundary conditions calculation. Hence, the boundary conditions can vary. Is such been reported instrumental observation?
I'm not sure what you mean by. Can you read that question again?
Yeah. So cosmological predictions are wrong. Was in one
They're
of
most likely not wrong.
yeah.
Yeah.
Mostly cosmological predictions are based on boundary conditions calculation. Hence, the boundary conditions can vary. Is such been reported in instrumental observation?
Okay, maybe I'll try to answer what I understood. So what do we even mean by it is cosmologically predicted to have 16%? So on an average, let's say I count all the mass which is there in the form of baryons, all the light I receive in across the wavelength. That's how I know that there are like these baryons, they emit in electromagnetic wavelengths, right? So whatever from radio, optical, X-rays, whatever light I'm getting, I convert that somehow in mass. I add up all the mass. Okay. And within the virial radius, let's say, or which is what is known as the boundary of the galaxy, are we getting 16% of the mass of the galaxy in the form of baryons? Now, if I again understand the question right, is the boundary wrong? Is what you're asking? If that's what you're asking, if the feedback processes are pushing the gas beyond the virial radii, then the observation should be able to detect, okay, if you go from, instead of virial radii, you go 2 times, you go 3 times, you should be at some point getting 16%, because on an average, even if you look at the intergalactic medium, one gets more or less, okay, at least at high redshifts, one gets 16%. In the intracluster medium within the virial radius, one gets 16%. So what is so special about these systems? What is happening?
Thank you. I think if you have further doubt, you can also like ask question, and even feel free to unmute yourself and ask. So is there any more question? I'll let them ask question. I'll ask a question by the meantime. In your these like four set of models, have you assumed any kind of baryon fraction, or is it important to like even assume some baryon? What is the mass budget, and what fraction of those it in this?
Mass budget is the output, if I'm not wrong, at least in the precipitation model. And I think the mass budget is the output in most of these models. I can't confirm about the cooling flow and the baryon pasting model, because that's what I'm least familiar with. But at least for these two models, it's the output. The density profile is the output. You integrate the density profile, you get the mass profile. I'll check. I can cross check and I can come back to you about this question. Okay. But my understanding is at least it should be the output, not the input. Yeah.
But even if it's output, then what is the number? Is it like 16%, or is it like 10%, or what is?
That depends. That depends what is a fiducial. Like I've used this word a few times in this work. Fiducial model, that depends on the what is the gas temperature boundary you have used. What is the T ratio of T cool over T free fall, or T free fall over T cool you have used in this work. So and even in isentropic model, what is the meaning of the fiducial model here? And even most of the fiducial model are tuned to some data. Okay. So maybe not the data sets I have shown in this work, but they are all tuned to some data sets. Baryon pasting is tuned to, actually this model was built for cluster scales. So it is tuned to clusters. But if you use the same model at galaxy scale with the exact same parameters, you won't get like cosmic baryon fraction. Even in the isentropic model, I remember from this, I think 2017 or 2020 work, it said they get much less than the baryon fraction. But there are free parameters which can always vary. Yeah. Which is not explored here for the time being.
That would also be a good observational. Do you think that would be also a good observational proof for tuning this models? Like if one assumes that, okay, we are just not being able to detect those baryons are there, and there is 16%, and we just trying to like match the 16% observation.
Okay, what you're trying to say is we don't care about the flexibility in the baryon fraction. We want all the baryons, and then what is the observation?
Yeah,
This
exactly.
is forward modeling here.
Like,
Yeah.
overproducing the observation or underproducing.
Yes, that can be done. That can definitely be done. And what my understanding is, you are going to overshoot everywhere, because most of these observations, I think I had it here. Yeah. Most of these observations indicate a lower baryon fraction than the cosmic baryon fraction. You'll get very, very bright, and especially X-rays. It's very sad that the sensitivity level is here for this mass scale. Maybe if you have slightly more mass, you don't have to restrict to this mass and this redshift. You can play around, maybe not Milky Way, maybe slightly more massive halos. Then the situation actually rapidly changes, because it's density and temperature, density square. So X-rays are probably one of the most powerful because they are density square. So one should be able to very quickly tell whether you have cosmic baryon fraction or not, but it dies very quickly when you go to the large scales. And a lot of the baryons are here, right? Because it's volume film. So if one is able to detect it out large area, you won't even be able, you should be able to not just tell the baryon fraction, you'll be tell exactly how it is distributed in the galaxy.
Exactly. Okay. And also like, I mean, is this profiles are assuming like there are some iron abundance, iron column density you had plotted.
Yes.
I mean, what
So
redshift, I mean, it's like metallicity of 0.3 solar metallicity
yeah,
and collisional
yeah,
ionization
it's
you have assumed, but
equilibrium.
yeah. So is it like, I mean, if we relax that assumption, does it change anything in the
Yeah, it will. It will change a lot of things, especially when you're looking at column densities. This figures will very crucially depend. Maybe not this ones as much. TSC, KSC definitely like it won't depend as much on metallicity, collisional ionization, equilibrium, but these ones will significantly differ, and that's what we are thinking is happening here. That we are forcing the model to be in collisional ionization equilibrium. And that's why this precipitation model is so below this predictions, not just, there's definitely Marmarquez wise. So we won't be able to tell till we explore. This paper is only about presenting the results, presenting the pipeline, first results. So we haven't explored the parameter space and what all can be achieved. It will be really interesting to see if one is even able to explain two observations with one set of parameter, and forget about like six. If let's say dispersion measure and this TSZ, even those two can be explained by one set of parameters for one model, and then you can test it for a third set of observation. Maybe it fails, maybe it works. I think that's how it should go. Yeah.
Definitely. I mean, one model should be able to like even like match multiple observations. Then that would be like our maybe go-to model.
Yeah, yeah. And that's why this pipeline is there. I hope it works out that way.
Yeah, definitely. It's a great work. Do we have any other questions from the audience? If not, then let's thanks Priyanka, and we had a great time hearing to your CGM adventure, and let's maybe hear more from you in the later times. And okay, thank you everyone. So we'll finish it up here. So thank you.
Thanks a lot, Manami, for organizing this and being here at such an odd hour. Yeah.
Yeah. Okay.
Thank you.
Thank you.
Bye.
Bye.